Hi, in this video I continue my work on the script for modifying hierarchical material files for DAZ Studio with Python. This part builds upon the previous parts, which I recommend to watch that you know how I've come so far. This part is about how JSON files are organized, Python's dictionaries, accessing particular data from the JSON file, a tuple, what actually to delete from the data structure, skipping code in a loop, accessing a dictionary with the get method, removing an element from a list, the call by reference concept, removing a key from a dictionary, and a very embarrassing beginner's mistake. Remember, I want to remove the Genesis 9 node and the here node's reference to the parent node for all DOF files which are hierarchical material assets. For the next step we need a bit knowledge about JSON and how it's represented in Python. In the JSON spec we find that a JSON file defines either objects or arrays. Objects are confined in curly brackets, arrays in square brackets. Objects are organized in string value pairs, while arrays only have values. In both structures, elements are separated by commas. If we have a look on what the document says about values, we see that a value not only can consist of elementary data like strings and numbers, but also of objects and arrays again. So a JSON file can hold nested structures, and we see those in our DAZ material file. It starts with a curly bracket, hence everything in the file is an object. We see string value pairs and that the value can also be another object or an array. In Python we have similar data structures available, and by importing our file using the JSON module, the JSON objects become dictionaries and the arrays become lists. Let's have a brief look into Python's dictionaries, and to show you I'm gonna be using Python's interactive mode. In the console I type pi and the interpreter greets me with a friendly triple-angled bracket prompt. First I define a dictionary, and already here the similarities to a JSON object are obvious. The confining curly brackets, the key value pair, and the delimiting colon. I put it into the variable a and confirm that's really in there by printing the content of a. I can simply access the value by putting the key in squared brackets. With the update method I can add a new key value pair to my dictionary. After that, the key A has still the value 12 and B has 13. I must be careful accessing non-existent keys, because that leads to an exception. My next exploration shows that we can define nested structures because our value is now another dictionary. And the result shows that the update method overrides existing keys. That's why it's called update. If I print only the key B, I still get a dictionary. But I can simply join the keys in the order of the hierarchy depth to get a particular value in my hierarchy. And now I can use this knowledge to access the data within our hierarchical materials file. Remember, we were about to write code that opens a file only if it's a hierarchical materials file. And in our materials file, we find an entry asset_info, which has an entry type which says preset hierarchical material. So I write a function that returns true if the file I opened is a hierarchical materials file. And because type is a nested element, I join two keys. Finally, I check if the value I've read is really the one in my file. Now, there's still one ugly detail in the way I access the elements in the JSON structure. Remember that I got an exception when I tried to access keys that do not exist? It's not very likely, but if I open a malformed DOF file, my script would crash. So I catch this exception and return false, because in this case I must skip this file. In the open materials file function, I add the call to the is_materials_file function and return none if it's not a materials file. And just a short reminder to get the type hints right, because now the function can return either a dictionary or none. Everybody working with my code should know this. It's always a good idea to refresh our memory about the concept. The last entry in my to-do list is save and conditional compressed save. That means I want my script to save the modified file compressed if it read a compressed file in the first place, and uncompressed if it read an uncompressed file. I need to store the result of my compressed check somewhere. Because a function loses all local data when returning to the caller, I must return the file type information. I introduce an is_compressed variable and take the file type check function from the if statement so that I have a value for my new variable. Then I add the is_compressed variable to the return values. And boom, we've just learned about the new data type, the tuple. A tuple is just a bunch of items, variables, stringed together. Separated by commas, they form a data structure I can treat as one entity. At the receiving end, I can split this entity, the tuple, just like I formed it, by comma separation. Let's quit the interpreter in the console and try out the script. I get the material file's content, which is a lot, and I get my compressed flag, which is true because the file indeed was compressed. And now I'm ready for the central step, the removal of the unwanted information in the materials file. The goal is to make it look like this, while it currently looks like this. I must get the node called nodes, which is an array, and remove an element from it. Because there are 3 items in the array, aka list in Python, I must select the right one by reading the ID key and check if its value is Genesis 9. Let's code this. I create a new function, delete unwanted code. The pass keyword is only a placeholder for now, because I can't declare an empty function in Python. Within the main loop, I call this function for each file. My new function will return false in case something went wrong during the removal, hence I print an error message. Also, I only want to process the file if I could open it. The continue keyword will cause the loop to immediately continue with the next item in files_in_dir and ignore the rest of the code in the loop. That's why it is important to place it before calling the deletion function. Also, if the deletion failed, the loop should immediately continue with the next item. I define a constant for checking if my object is the one I search for, the one with ID Genesis 9. I add false as default return value, which I'll overwrite with true in case of success. I plan to read the node hierarchy scene nodes, which will return a list of dictionaries in Python. Every list element is a dictionary having an ID entry I must compare with my newly created constant. The variable I store the subnode's content in is a list of dictionaries. Now I access the nested node, and because it could go wrong, I put it in a try except block. In case I can't access the subnode, I return the result variable, which is still false. Because I got a list, I can iterate over its elements and retrieve the ID node. Because I iterate over a list of dictionaries, scene_node is a dictionary. Therefore, I can use the get method to get the value of a given key. The get method has an advantage over direct indexing. It does not throw an exception if there is no such key. Instead, it allows me to define a default value. I didn't specify one, and so the default value is none. Instead of having an except block, I check for scene_ID being none and continue with the next scene node in case we have a problem there. Time to try it out. I set the return value to true, otherwise my main loop would skip, and then I start my program. I got something back, but since it's a structure, it's somewhat hard to read. Python offers a nicer print function, pprint, I can use after importing it from the pprint module. Replace the original print with pprint and start again. Here they are, all 3 scene nodes. Now that I know that I'm on the right path, I compare the current scene ID with my unwanted constant. If it's my unwanted node, I remove the entry from my scene node list. When trying it out, I expect the node to be removed. Yes, it is. You can still compare it with my last run without the remove statement. There is one last important concept in this project we should talk about, just to make sure there are no misunderstandings. You saw that my code did remove the unwanted element from the list. It did so by calling the function delete_unwanted_node and passing the JSON-like structure to the function. Within my function, the JSON data got stored in the variable called content. The content variable I do not need for very long, because already in line 56 I fetch some details from my JSON data. And on it goes with the variable scene_nodes. And from there I delete the element. That's far off my original mat_content variable. Moreover, I didn't even return anything else than a boolean to the main loop. And yet still I can print my mat_content, having all the changes I did somewhere else. How can it be? Well, I have my main program with a function call, and I have my function. And in my main program I created a list from a JSON file using another function, but that doesn't matter. With the function call, you might think we duplicated the list and passed it to the function. There, one element in the list gets changed. At this point, we'd have two lists in memory that differ. So we'd have to return the list to our main program and overwrite the original list. Your thought is nice, since there is indeed a concept like this named call by value. If you give it a second thought, you'll realize that it would not be very CPU and memory efficient to always copy a list. Without JSON, this wouldn't make much of a difference, but just imagine a list of vertices in a 3D model. There's 1 million vertices in this model. But that's not how it works in Python anyways. In my code, I don't replace the list, and I do not even have it as a return value in my function. You see, the list gets stored only once in memory, and since the location in memory is known, the interpreter can work with the address in memory instead. So wherever in my code I refer to the list is actually a reference to the memory location. In reality, it's a fair bit more complicated, but you get the gist. My function directly changes the list, and my main program directly reads the element from that very list. This concept leads to some implications, of which the most important one is aliasing. If A is a mutable object like a list, and I assign A to a new variable, every change I make to that variable automatically affects also A. The aliasing can happen all over my code. Here, if I had a function B, it could also change my list. The way of working with only memory addresses is called call by reference, and Python does it automatically for all objects. However, we should be aware that different types of objects are treated differently. Python knows mutable and immutable objects, and the latter we can't change. You've heard it right, you can't change a string nor a tuple object. In this example, I'm trying to change the H of hello world to a C, and the Python interpreter bites back with an exception. Same applies to a tuple. It is simply not possible to change it directly. That behavior renders passing of immutables to quasi-call by value. If I really must change immutables, I have to make a copy, like you saw it before with the mutable. Fortunately, my node deletion code does not require any copying, and so I can rely on the function really changing the only instance of the JSON content. I go on with deleting the JSON's reference to the parent scene node. If there is a parent entry and it contains Genesis 9, I delete the entry. That's the pop function. The in operator, also called membership operator, returns true if the specified value is present in the object, just like you would read it as a human. And because scene_node is a dictionary, I remove the key value pair with the function pop. That should be it. I give it a try, and it fails. Why didn't it remove the parent entry? I gotta fix this. I investigate by checking if my loop goes over all scene nodes. A quick test shows that my loop iterated only over 2 items, the Genesis 9 node and the James Hare node with the longer number. Of all things, the interesting element got skipped. But that's nothing to worry, I just made a pretty embarrassing beginner's mistake. Let me explain. Every element in the list has a position within that list, an index. Our for loop internally has an index of the current element. At the beginning, the index is 1. Yes, I know the index is actually 0, and in reality everything is much more complicated, but let's not split hairs, really. Already in the first iteration, the condition for the deletion of the unwanted code is met, and it gets deleted. That causes the elements to be rearranged. Our first element is now the James Hare node with the Genesis 9 parent reference. The next line is the continue statement, which causes the loop to increment the index. And there's the problem. Our rearranged element 1 in the list never gets hit because our loop index does not reset. Instead, it's working through element 2, which is our last element in the list, and we also observe this in our debugging output. And the moral of the story: never ever delete an element within a loop if it's in the actual object you iterate over. Luckily, the fix is easy. I introduce a new variable which serves as an intermediate storage of the node I want to remove. Outside the loop, when all elements are checked already, I remove the node if it was found. Finally, I only return true if something got deleted. Yes, I didn't check separately if the parent key got deleted, but that's how good it is for now. And let's check what happens. Oh, looking good. We got our parent node deleted, we got the reference to Genesis 9 deleted. The remaining data also looks okay. It compares well to my manually fixed file from part 1, so I declare this job done. For further testing, I remove the break from the main loop, and my script does the removal of the unwanted information for every file. Look how fast that was. Looking through the results, I find one interesting output. Here it tells me that it can't delete the data because it didn't find a parent. That's a good sign, because also in part 1 I did save a corrected version of a materials file, so my script can also handle the case if I accidentally execute it twice on the same folder. And this concludes part 2 of editing DAZ Studio DSON files with a Python script. See you in the last part.